Okay, this whole year has been about chemistry, but pretty much it's been about how do atoms bond together with other atoms? Do they share their electrons? How many electrons do they share? How many electrons do they have in their outermost or valence orbital? If they're metals and nonmetals, how many electrons do they lose or gain so that they can become isoelectric to a noble gas, so that we can figure out what is the ratio of NaCl in a 1-to-1 ratio, or calcium chloride, CaCl2, which is in a 1-to-2 ratio. Right now, we're about to start a completely different chapter of chemistry, literally called nuclear chem. This is about the nucleus. This has got nothing to do pretty much with the electrons. This is about some strange kinds of atoms that are not stable, atoms that are dangerous for us to be near, atoms that can kill you, more or less. And it's about the nucleus. So we're going to do a quick review about what we understand about atoms, and then we're going to jump right into this nuclear chem. Now, nuclear chem number one, it's about the nucleus, and it's kind of a weird world. Atoms have neutrons and protons in the nucleus. Neutrons are neutral. Protons are positive, flying around the outside of the negative electrons. All atoms are neutral. They have the same number of positive protons as negative electrons. Number two, the atomic number is the number of protons. But since the positives equal the negatives, it's also equal to the number of electrons. The atomic mass in high school is measured in AMUs, or atomic mass units, and a proton and a neutron both have 1 AMU in mass, approximately. That means the mass number is the number of protons plus the neutrons total in AMUs. For example, my favorite element, mercury. It has a mass of 200.51, which rounds to 201 AMUs. That means there are 201 protons and neutrons combined. Now, the atomic number 80 means there's 80 protons. So if the mass is the protons plus the neutrons, if we take away the protons, the leftover would be just the neutrons. So from a periodic table, from our periodic table, you should be able to determine the number of protons, neutrons, and electrons in any atom or any isotope. Now, every atom has a unique number of protons and electrons. If you happen to be number 12, you have 12 protons, you must be magnesium, there's no choice. If you have 29 protons, well, if you look at the periodic table, the only atom with 29 protons is copper. 29 protons means you're copper. And if you have 92 protons, you're at the bottom of the table, you're going to be an element named uranium. Every atom has a certain number of neutrons, but there are isotopes of every atom. So there's more than one kind of copper. There's more than one kind of uranium. There's even more than one kind of hydrogen. Hydrogens all have one proton, but some hydrogen atoms have no neutrons. Some hydrogen atoms have one neutron, and a few kinds of hydrogen atoms have two neutrons. So they have different masses. Those are called isotopes. There are isotopes that are chemically identical, but they have a different mass because there's a different number of neutrons. Now, this is clipped right out of your periodic table. In group 1, period 2, is lithium. Lithium is atom number 3. How many protons, neutrons, and electrons are in this atom? So if we look at this, the mass 6.941 AMUs is going to round up to 7 AMUs because we're friends, because it's high school, 7 AMUs. Out of those 7, 3 of them are protons. There's no doubt because it's atomic number 3. So how do we figure out how many protons, neutrons, and electrons are there? Well, the lithium mass, which is the protons plus the neutrons, is 7 AMUs. If we take away the protons, 3, that's going to tell us how many neutrons we have. 7 is the total mass, 3 are the protons, 4 must be the neutrons. So these are 2 atoms of carbon. One is called carbon-12. That's the isotope that's actually kind of normal. 99-point-something% of all carbon is carbon-12. But there's also carbon-14, a radioactive carbon. Now, radioactive is nuclear chem. We'll get to what that means later. But this carbon has a mass of 14, not 12. Carbon is carbon is carbon. Carbon has 6 protons. But sometimes the mass is 12, sometimes the mass is 14. So for carbon-12, 12 means protons plus neutrons minus the number of protons. That's going to tell us how many neutrons are in carbon-12. So For carbon-14, that means the mass of carbon-14, protons plus neutrons, is 14 AMUs. Minus the protons is still 6. That's going to give us the number of neutrons. So for carbon-12, 12 is the mass, minus 6 protons. That means there's 6 neutrons in carbon-12. That particular kind of carbon, that isotope of carbon called carbon-12, has 6 protons and 6 neutrons. Now for carbon-14, carbon-14 is still carbon. It has 6 protons, but 14 minus 6 means this particular kind of carbon has 8 neutrons. That's different. Now, there are 2 isotopes here for phosphorus, phosphorus-31 and phosphorus-30. Now, phosphorus-30 is actually the radioactive kind. Phosphorus-31 is more or less stable or normal, but there are some phosphorus atoms that are radioactive. That's the nucleochem part we're going to get to in a while. Both of them have different masses. Phosphorus-31 has a mass of 31. That means there's a total of 31 protons plus neutrons. For phosphorus-30, that means that this phosphorus nucleus for phosphorus-30 has a total of 30 protons and neutrons total. They both are going to have the same number of protons because phosphorus on the periodic table is number 15. And that means phosphorus-31 has 16 neutrons, but phosphorus-30 is going to have 15 neutrons. Now, it seems like neutrons are neutral. We never really talk about them much. It shouldn't make much difference. But as it turns out, if your proton to neutron ratio, or neutron to proton ratio actually, is not what's considered normal, you're unstable, you're radioactive. Now, most atoms are perfectly stable, but there are some that are out of sync. They have the wrong number, so to speak, of neutrons. And that makes them what's called radioactive and actually very dangerous to humans and other living things. Now, there's 118 elements on the periodic table that we know about. That's about it. That's all we know now. There are about 1,500 isotopes. That means every atom has got multiple numbers of kinds or flavors. Each one has different numbers of neutrons. So for hydrogen, there are 3 isotopes. Hydrogen that has no neutrons, hydrogens that have 1 neutron, hydrogens that have 2 neutrons. There's 3 isotopes of hydrogen. Now, out of the 118 elements, there's about 1,500 isotopes. Now, out of the 1,500, almost all of them are stable. If you bumped into them on the street, you'd be perfectly fine. Put them in your pocket, take them home, no problem. But about 150 of these 1,500, about 10%, are unstable. Their neutron to proton ratio is funky. And because it's funky, they're unstable and they're going to emit parts of their nucleus. They're going to just spit it out in order to change this ratio to stable. And the stuff they spit out of the nucleus, that's called radioactivity. And it comes in a lot of different kinds. We'll talk about that. Now, fixing the neutron to proton ratio means they're going to emit parts of their nucleus. And this stuff that they emit is called radiation or radioactive particles or radioactive energy. And it's going to change the neutron to proton ratio. For the atom, it's going to make them more stable. For humans and other living things, it's going to be death, right? Radiation can kill you. A little bit of radiation, you might be able to survive through, right? You disrupt some of your cells and now you replace them. But if you get radiated too much, it can kill so many of your cells that actually it can lead to your death. Okay? Now, this is what's called the band of stable neutron to proton ratios. If we took all the atoms, all 1,500 of them, 1,350 are going to be along these dots. These dots all represent literally individual atoms. So on this graph, if we took element number 30, which is zinc, and we rolled out to here, zinc is going to have, forgive me, this is the number of neutrons. If we took element 30, which is down here, zinc, and went up, the number of neutrons is going to be in here somewhere, 30, 37, 38. Atoms have this atomic number and this number of neutrons, and all the stable atoms are in this zone of stability. This line represents a 1-to-1 ratio, just literally 1-to-1. When atoms are little, really little, under 20, the 1-to-1 ratio is pretty close to stable. But once they get medium or big size, it's actually a bigger ratio, 1.5 neutrons to 1. That's stable. Now, there's a lot of different stable isotopes. There's 1,500 isotopes, and most of them are stable. If an atom has a different number of neutrons to protons, if their dot is over here where this arrow is on the graph, or below 1, or anywhere in here, that makes them unstable. And if that's where they are, if that's their atomic number of protons, and that number of neutrons would make them unstable, make them radioactive. Now, if we look at table O, there are 6 kinds of radiation that are listed here. Okay, most of the radiation is particles, but it can be just energy as well. And we need to be able to look at table O, read table O, know what table O means. And so let's go through these. We'll go through the names quick, and then we'll go through what all of this means. Alpha particles are the first listed. They're listed in alphabetical order. Alpha particles, type of radiation. Beta radiation, beta particles, another kind of radiation. Gamma rays or gamma radiation are another kind of radiation. Neutrons can come out of the nucleus. Protons can come out of the nucleus. And positrons. Now, there's a really weird particle we've not talked about all year. A positron is sort of like an electron, but with a positive charge. And it comes out of a nucleus that's unstable. So we have 6 kinds of radiation. We're going to go through them really slow. Now, each type of radiation is going to have mass. Now, we're going to round this in high school chem, but they're going to have mass, they're going to have a charge, they're going to have symbols, and then we're going to have what's called penetrating power. How bad is it? If you're near alpha radiation, can you protect yourself? Can you hide behind something? If you're near beta radiation, can you hide behind something to protect yourself? The penetrating power is how much energy these particles have. First one is called alpha particle, and according to table O, the number 4/2 means that has a mass of 4 AMUs. Alpha particles are actually the largest radiation particle. The 2 on the bottom, 4/2, if we look at this symbol right here, 4/2 or 4/2, this little symbol is called alpha. That's the lowercase Greek letter. It's a really weird thing, but alpha particles, they're large. They are mass of 4. It's 2 protons and 2 neutrons together. It's a big chunk that comes spitting out of certain atoms. As it turns out, the helium atom nucleus happens to be 2 protons and 2 neutrons. So sometimes the symbol we use is a 4/2 because the alpha particle has the same sort of parts as a helium nucleus. Now, if you're a large atom of uranium or thorium or something like that, and you spit out an alpha particle, you're not spitting out helium atoms. But the particle you spit out is a mass of 4, made of 2 protons and 2 neutrons. And we use this 4/2 alpha or 4/2 to symbolically represent that. Symbolically, it's not a helium nucleus. Now, because there's 4 charges, because there's 4 AMUs and 2 of them are positive and 2 of them are neutral, it has a net charge of +2. The next particle is called beta particle. Now, in high school, beta particle has no mass at all, but it does have a charge of -1. Now, as it turns out, beta particle has this first symbol of 0, -1e. The number on top is the mass, 0. It's approximately 0. It's not 0. And the charge is -1. The E stands for electron because a beta particle is very, very much similar to what would be an electron. Now, it's not an electron. Electrons fly around the outside of an atom. This is something that's being emitted from a nucleus. The second symbol there is 0, -1 with that little lowercase Greek b. That's the beta symbol. Now, its penetrating power is much stronger than alpha. I'm going to show you a really cool couple of pictures soon about the penetrating power. Alpha particles are fairly weak penetrating wise, bad for you if they get in your body, but they're hard to get in actually. Beta particles, right through your skin. You're in big trouble. Beta particle is very dangerous, and we use this symbol. Now, gamma is strange in a sense because it's got no mass, literally. It is a zero mass, and it has no charge. The symbol there is a lowercase gamma, Greek letter, the third letter of the Greek, 00 gamma. It's actually not a particle. This is electromagnetic radiation or energy, and it's very hard to get away. If somebody's shooting you with gamma rays, you're probably going to die. There's just no escape. They go through everything. They're so unbelievably powerful. So gamma radiation is the third kind of radiation, and it's the first one that's physically not a particle. It's literally just energy. Now, neutrons, you know neutrons. Neutrons can get spit out of the nucleus also. They have a mass of 1 in high school. They have no charge, and we have a cute little symbol, 10 little n. The little n stands for neutral or neutron, and we don't have to worry about their penetrating power in high school. Sometimes you can spit out a proton. Protons, you know also, they have a mass of 1, they have a positive charge. The symbol is 11 capital H because, as it turns out, most hydrogen atoms have no neutrons, so they have basically, they're just a proton. Remember in acids, P plus 1 is a symbolic representation for a proton, which is an acid ion, because once a hydrogen atom, which is a proton and an electron, once the electron's transferred away, all that's left is the hydrogen ion, which is really just a proton. Or we can use the symbol 11 little p for proton. It has a mass of 1. 1 on the bottom means 1 proton, which gives it the positive charge. And then the last symbol, this is really weird, positron, really weird. Positron's kind of like an anti-electron. It has no mass in high school. It has a positive charge opposite of the electron, and it's 0 positive 1e because basically it's a positive electron. It's not an electron, and there's no such thing as a positive electron. It's called a positron. It's really weird. 0 positive 1b, so positron, and its penetrating power will be similar to a beta particle. Pretty bad. You don't want to get near positrons either. Really bad for you. Now, here's a good representation of what is the penetrating power. There's 3 radiations down the side, alpha, beta, and gamma. And if you were hiding behind literally a piece of paper, hold up your reference table, alpha particles get blocked by paper. You could protect yourself if somebody's trying to shoot you with alpha radiation, hide behind a piece of paper and run away. Now, if somebody's shooting you with a beta particle, paper's not going to help. The beta particles go right through the paper. And actually, they can even get through metal and wood. You'd have to be behind a really thick wooden door, or you might even need some lead metal to protect you. Lead's much denser. Now, for better or worse, if somebody's shooting with gamma particles, gamma radiation, not particles, there's nowhere to hide. The gamma radiation can get through even fairly thick lead because there's so much energy coming out, and it's going to get you. So just stay away from gamma radiation. In this other picture that I'm going to show now, you can see alpha, beta, neutron, and gamma. They've added neutron particles as well. Alpha particles are blocked by paper, so you're kind of in the clear. Beta particles obviously go through paper, will also go through you and maybe get through some metals, but not all. Neutron's another radiation that comes shooting through, easily goes through paper, easily goes through you, where it does a lot of damage, and that's not good. Neutrons can zip right through metal also, but they're blocked by water. Now, gamma radiation, the one on the bottom that shows in the waves, actually the gamma are not particles, and they can go through paper and people, metal and water, through concrete, and even get through lead. What stops gamma radiation? Pretty much nothing, right? So as far as penetrating power, in the Greek alphabet, ABC is alpha, beta, gamma. Alpha is weak, beta is strong, gamma is destruction. Now, radiation is emitted, given off, by unstable isotopes, atoms that have a different number of neutrons than normal. And they do so in an attempt to become more stable. Okay, it just happens. Emitting different types of radiation will change that ratio in different ways. And we're going to see about how emitting an alpha particle changes a nucleus compared to a beta or positron or something else. Some isotopes can make a single change. You know what? I don't feel so good as an atom. I'm going to emit an alpha particle, blah, and I become perfectly stable. Sometimes it's one change and you could be stable atom, stable isotope. Sometimes it takes more than one change. Some isotopes make two changes. Some make many, many. Now, the type of radiation that comes out is very well understood by scientists. The amount of time it takes for this process to undergo is also very well understood by scientists. It's the same here, everywhere else in the world. It's the same on different planets. The radiation process, the emission of radiation, is very well understood. Now, as it turns out, nothing can make this go faster or slower. Remember we learned about in kinetics, if you heat things up, you can make the reaction go faster, and if you make it cold, it slows it down. Nothing changes the radiation emission process speed. It just happens, and it happens on its own. You can't stop it, you can't start it, you can't hurry it, you can't slow it. It just happens. It's natural. It's normal. You don't want to be near it, but it just happens. Now, when a nucleus emits radiation, the neutron-proton ratio changes and it becomes, ready for this? This is really weird. It can become a different kind of atom. By changing the number of protons in the nucleus, and that happens when you emit alpha particles, you change the number of protons. When you emit a beta particle, we'll see that changes the number of protons. When you emit protons, that changes the number of protons. When you emit positrons, that changes the number of protons. When you change the number of protons, an atom can become a different kind of atom. And this is crazy, right? This is like a dog. You put your dog to bed at night, you wake up and you have a cat. How the heck did that happen? This is how crazy radioactivity is. Radiation emission makes one atom become a different. Now, this process is natural. It's called transmutation. Atoms can transmute or become different, okay? Or it's called radioactive decay. When an atom is radioactive and it decays, it changes, it becomes a different kind of atom. Crazy, crazy. All right, we're going to stop there for this first class, and then we're going to look at this next class. And